Are you using YouTube for this class at all?
Yeah.
Yeah. So far, is it working for the most part? Yeah. Cool. Because I don't go and watch my own videos for a number of reasons. One of which is I don't want to get mad at myself for saying stupid stuff. So how's it going, everybody? Good to see you. Thanks for coming back. No quiz today, so you're off the hook. Don't worry about it. Couple procedural notes. Number one, you have your quiz number one back. Your homework one I haven't graded yet, but I'll grade it as soon as possible, hopefully by Thursday, and I'll email that back to you. And online, we have homework 2 available now, which not everything you'll be able to answer yet because we haven't gotten through everything yet. But if you want to give that a try, it's probably a good time to start trying sooner rather than later because it makes you use Latent. And if you haven't used Latent yet, there'll be some growing pains, I think. And again, I'll remind you that Lou is your first option for help with Latent syntax. And if for whatever reason she can't help me, have me come to me. And again, just the division of labor. This is an odd thing. We're a 900 level course, so to make sure that we're all cool with everybody, Lou is tech support more than I am grading. So I'm the one providing grades, but she's going to help. And that'll help her learn about how to teach this as well. So, right? Yes. Any other thoughts, questions? Okay. It seems like last time was like forever ago. So it's been a while, hasn't it? What do you remember from last week? Factor analysis. Yay, factors. Yeah. Standardized loading? Unstandardized loading? Let's just go through this. The factor analysis, the confirmatory factor analysis. It assumes the factors are normally distributed, although we haven't really explicitly said that yet. It also assumes that error, or the residual, is normally distributed. So when you put those two together, you get this idea that the data have to be continuous and normal. And once again, what we have in a factor analysis is a series of simultaneous regression lines, right? And we call them simultaneous, or yeah, I guess we call them simultaneous. Simultaneous because we're doing this all at once in one estimation. We can't, because we didn't observe the factor, we can't just take one line all by itself and create the parameters, doing separate regressions. This is going to be more of a note when we get to path analysis, because path analysis is a bunch of simultaneous regressions as well. It's just not every one of them has the factor in it. It'll have, some of them will have a factor, some of them will have predictor variables, some will have other parts as well. So in your way of thinking about this, this is sort of priming you to get used to thinking we're doing a bunch of simultaneous things because of the nature of the data that we have. We have to do it in factor analysis. It's a good idea doing it in path analysis. If you did path analysis, what am I getting into? Going on a tangent here, but I'll try to make it short. If you had a bunch of simultaneous regressions, but instead of F, you had like a series of predictor variables that you observed, you could separate those. It wouldn't necessarily penalize you too much. Do a separate regression for each. But there are some benefits for doing it simultaneously. We can get to that. We'll get back.
So if we have like sample of 200 with like a quiz of 35 items, that means we have almost like 7,000 regression equations.
No, the equations are all for the items themselves in the factor analysis. So the equations themselves, we abbreviate them by person, right? But so what we typically do is we just lump the observed items together, and we just say all the people who have this item. So you'd have, if you have 35 observed items, it'd be like 35 regression equations. I can see where you'd like to, you could think of it as having a lot for each subject, but really ultimately we just sort of abbreviate across the subjects for the students.
But is there like going off from this point, like, is there a way or statistical procedure that we can estimate the
individual subject who took that item based on information we have?
You want to get the
Subsequent-
factor score from the person?
Yeah, for each person. Like
Yeah.
Subsequent.
We're going to get there. Yeah, we're going to get the factor score for each person, yes. But the predicted value, you'd need to know the factor score for each person. So if you wanted to go and say, person 1, if their F was a 2, you'd come up with a predicted value for that person. You could. Ultimately, you need the factor score to do that. But we'll get to that shortly. Other thoughts or questions?
Yeah, why do they do researchers say that the more items you have, the more sample size you need? So this is not related to CCP.
It's not necessarily related in CFA, although really what's happening is the more items you have, the more parameters you have to estimate. And so there's this thing, those of you who took multivariate with me, that there's this idea that when you have a simultaneous set of equations, what it is a multivariate model. And a multivariate model, particularly with a normal distribution, uses a multivariate normal, so it's got this covariance matrix. Right? So this covariance matrix is number of items by number of items. And actually, as we're going to see pretty soon when we talk about model fit, we need an estimate of that all the elements of that covariance matrix. So every time you add an item, you add a variance. You add a mean, just one. But you add a covariance with all the other items as possible. Right? So when you have 5 items, your covariance matrix will have 5 times 4 divided by 2, 10 unique elements. When you have 6, you'll have 6 times 5 divided by 2, you'll have 15 unique elements. So by adding one more item, you just added 5 more things to estimate. It's called the curse of dimensionality. As the number of observed variables goes up, the more things you have goes up linearly. The things that you have to estimate goes up non-linearly. So sort of an increasing exponential, not quite an exponential, combinatoric function for it. And so that's part of the reason why when people say you have a lot of items, there's a lot of terms to estimate overall. It becomes harder. Now that's not true of all models. It's not true of everything else. Ultimately, the CFA model, whenever you add an item, if it's only measured one factor, because of the constraints you're putting on this matrix, which we're going to see today, really you're just adding a factor loading, a mean, and a variance. You're adding 3 parameters, not parameters with all the other items. So it goes up linearly as well. So if the items fit the model, it's fine. It's big if.
And when you say this is related to the idea that the error variance will increase because the covariance is with other items?
Not necessarily. The idea of adding parameters is just a function of what's in the model for each regression equation. Model fit, though, yes, that is where you may have to. If I find it's very difficult to get a lot of items to fit a single factor. You have to have a really well-defined factor for that to happen.
So you are implying that there is not a typical, but an approximate number of items, like based on the empirical research.
What is a good number?
Yeah.
What's a good number of items? It varies widely. It varies from a minimum of 3.
But
the upper limit is quite a bit, and it depends on. So let me put it this way: if you're using a CFA model approach, if the research, and this is where your homework 1 happened. You all looked at your studies before. How many of your studies use CFA or some other type of technique like that? Calibrate it, or IRT. In your homework 1, I haven't looked at them yet. No? You got 2 here, EFA. What's that? Principal components, PCA. So, Craig, you had a CFA.
One of the validations.
The validations. Bisha, you had a CFA. So you had measurement model. Mayumi, I know I looked at yours. You had a measurement model as well. What I'm saying is, if you see a published study that has a measurement model, then you assume that fits well. And so there's a sort of an extra penalty to check model fit to see that happening. And what I typically, let me just put it this way, anecdotally, my opinion is that those have fewer numbers of items than if you would have used EFA or PCA. And the reason for that is the strictness of the model fit requirement. So what is that number? I don't know. It varies widely. The EFA and PCA, how many items per factor did you have? 4?
9, 9, and 5.
9, 9, and 5?
Somewhere around 5.
Somewhere around 5. 6. What's about, and then Craig or Bishi, what did you have in your, how many items per factor on it?
Very
Very.
perfect. I think smallest factor was like 4, highest one was like 9.
4 to 9.
So they found like there is only one factor in this.
Okay, 8 items. So you get a sense just anecdotally here. What's interesting about that is the methods we're using, particularly if you compare them when we get to IRT. You'll see in IRT, there are tests where one factor is 80 to 90 or even more items. Right? And again, I'm going to make an argument it's not model fit. There's not really good methods of model fit that people are. There are good methods of model fit in IRT, but people aren't using them. Don't understand. So ultimately, it becomes this. It's a philosophical question. When you create a construct, when you come up with the idea of this label of a variable that doesn't exist, you have to write items that measure this construct. And for most construct, there's only so many ways that you can write an item. Right? I don't know if you're in education, you're doing cognitive testing, you're trying to test parts of fractions, right? Infinite number of items, because they're essentially interchangeable, right? The number 9 versus the number 2 in a fraction probably isn't going to make a difference if you create it with certain specifics. But when you talk about measuring something like happiness or openness to experience or something that, anyone have agency in there? That's the word that agency, which yesterday's agency is today's grit, right? Or something like that. Anyway, these labels, there's only so many ways that you can measure that. Write an item to do that. So you're sort of, on one hand, constrained by model fit, and on the other, constrained by just philosophically, how many ways can you ask the question, right? Or how many features of the factor really get implied by that. So I hope that helps a little bit more. Anybody else? Yay, CFA. Actually, I like CFA better. It just never, it's never really realistic for the data. That's the other thing. I'm gonna we're gonna do some CFA love and compared to my EFA hate. But in the back of your mind, you should realize the question of, yeah, but I've got these categorical responses. Those aren't really continuous, are they? Right? So just have that in the back of your head. Okay. So I think we left off with the model predictions. I was talking about the tracing rules. Like if you wanted to talk about what the model is doing, when you go and write this CFA model, there are certain very specific things you're implying about your data. And that's what puts the C in CFA, the confirmatory in CFA, saying, if you say I'm going to confirm this is the structure of my data, then it's going to tell you a little bit about what your data should look like, what the means should look like, although those are sort of just automatic. What the variance should look like, those are also usually automatic. But more importantly, what the covariance or correlations look like. And so with that, the correlations and covariance are the parts that we really want to talk about. If we're talking about the covariance between a pair of items that measure the same factor, again, it's the loadings times the loading of the item, the first item, times the variance times the loading of the second item. And this is where I pointed back to our path diagram. We said sort of trace the root from each and multiply the parameters. So it's lambda 1, 1. There should be a variance with this factor up here times lambda 3, 1. Gives you the variance or the covariance between those items in the same factor. Similarly, items on different factors, you'd have lambda 1, 1 times the covariance between the factors times lambda 4, 2 to get lambda 1 to lambda 4. So this is going to be incredibly important in that we're going to use our model fit. We're going to base our model fit on that covariance matrix. Right? We can go and generate, or we can go and estimate a covariance matrix from our real data. We can see what that happens to be. We can also go and estimate our model, and we could fill in a covariance matrix with what we expect our estimates to give us. And the discrepancy between the covariance that we see in our data and the covariance that we expect with our model parameters is going to give us our measure of model fit. If there's very little discrepancy, if you could take one and subtract the other and get zeros, model fit's great. If there's something not zero there, now you've got to evaluate, is that just noise, is that chance, or is that something else? By the way, one last part on the bottom part of this slide, the variances themselves, the variance for a given item is if it only measures one factor, it's the square of the loadings times the variance of the factor plus the variance of error. Right? Variance of error, this is our unique variance. It's its own parameter. So whenever you see a function like this where there's a plus, that means essentially this is going to come up with the exact number of the variance, right? Because this part comes from the factor, and this part comes from error, and they have kind of sum to that total value. So we'll get to that. Okay, so here comes the matrices. Don't you love matrices? I've tried to minimize them as much as I can. But let's think of it this way. There is this is the quintessential matrix equation of CFA. Right here. If you had to memorize any matrix equation, use this one. You're going to get a tattoo of a matrix equation. This is a good one. Right? I may or may not have this tattooed somewhere. Clearly not on my arms or my face. I might do the linear equations or what they call the normal equations for my face. X transpose X inverse. Probably not. So the matrix equation, what are we talking about here? Oh, I've got it all on my slide. I can just point to it. Okay, lambda, this is a capital, sigma is our covariance matrix. This is capital lambda. This is capital lambda transpose, right? Capital lambda is the matrix of factor loadings, right? So what does it look like? It's right here in the middle. It's this number of items is the number of rows, number of factors is the number of columns. And if there is a factor loading there, if you've estimated, if you think that factor measures that item, you'll put the loading parameter there. If not, you'll put a 0, right? So this tells us factor 1 is being measured by items 1, 2, and 3, but not 4, 5, and 6. And factor 2 is not measured by 1, 2, and 3, but is measured by 4, 5, and 6. Right? So it's just an arrangement of numbers. On the right-hand side is the transpose of it, right? Or in multivariate, they talk about transpose. I know, Michael, you've seen it. Right? So it just takes that matrix and just swaps the row and the column position, right? So it just moves it like this, right? So it's the same matrix, moved differently. We do that just to make matrix algebra work. This is not going to be a deep dive into matrix algebra. But I'm going to say this because you do see these show up in papers sometimes and in other places. The transpose in matrix algebra, just for your information, matrix multiplication is one of these weird things. To do a matrix multiplication, the number of rows of the preceding matrix have to be equal to the number of columns of the post-multiple matrix. And so that's where transpose usually becomes handy. It just sort of makes the size of the matrices line up to make a product. All right. So here, matrix of factor loadings, that thing transpose. This capital phi is PHI, is the, I guess in other countries, phi, is that other parts of the United States? Phi. Phi for us here, for whatever reason, but then again, we use inches. So, we're different. We just like to express how crazy we are in things like Greek characters. That is the covariance matrix of your factors, right? So what does that mean? When you estimate these terms, when you estimate the factors, if there's a two-factor model here, there's going to be a variance for each factor and a covariance between the two. So that is the first part of this equation, lambda phi, lambda transpose. The last part, the matrix, this is capital psi, PSI, phi, psi, right? PSI, what's that?
Not C.
Not C.
Okay.
Not C, no. Phi is phi, but not C. Exactly. This is the matrix of residual variances down the diagonal. Right, so each one of these values right here represents the unique variance or the residual variance, what's left over for each item after you've accounted for what the factor does. The off diagonal that we're going to talk about right now is 0, but there are spots there that represent the residual covariance between items, right? So if this were to have a number there, it would talk about how much covariation there was left over after you predicted the item with the factors. This would be like a residual or a unique covariance, another way of talking about it. But this is unique variances here, and so forth. We'll get into those error covariances a little bit later. I mentioned this last time. Those are sort of they weaken your argument for measurement, though, right? It's the idea that if you think factor 1 measures items 1, 2, and 3, it should describe all the covariation between them. If you put a parameter right here, because this is added to this other matrix right here, that means you're going to perfectly recover the covariance between those two items in the data, right? Which sounds good because you want to recover it, but conceptually that means that you've said basically factor 1 is not just the only reason these things covary. It's factor 1 and something else, right? Which really you want to try to stay away from. If you're saying factor 1 is happiness, and you're like, yeah, but I put a residual covariance between these items, really means it's happiness and something else. So, how we doing?
On the error,
Yeah.
the item error matrix,
Yeah.
what are rows and columns?
Mm.
Are those items?
Pardon me, those are items by items?
Right.
This is going to mimic the size of the covariance matrix, which is also observed items by observed items. Pardon me, thank you for asking. So what is this first block right here? That is sigma. That's our matrix of what we found in the data. Or actually, in this case, it's what we're predicting is in the data. We're saying this is what's true because of the factor model. And that's how CFA gets the C, right? That's how it gets the confirmatory. It says, you tell me the pattern of factors, which factors load on which items, and I expect a matrix to give me a form that looks like this. Now, when we go forward, this predicted covariance matrix, this is what comes from the model, is made up of all the components that you see, right? This is all the factor loadings, all the factor variances, the factor covariances, and the unique variance. Right? So this is just putting it all the same. This is the product of all these, the product of these three matrices plus that. Gives you what's on slide 15 here.
And this is in the case that the determinant, the covariance, the variance covariance matrix is not zero.
So the determinant of the covariance matrix talks about effectively another way of describing that is an index for what the dimensionality of it is. If the determinant is 0, it means it says that there's a linear dependency in the data. So that means effectively one item or some combination of items gives you another one. Where does that happen usually? Like if you put item 1, item 2 in their sum in the same covariance matrix, you get a covariance matrix with a determinant of 0, and that's because you can find the third column of the data from the first two. But yeah, for right now, this actually works for even if we had that, effectively this could work, although we probably wouldn't get numbers out of the computer. So we don't have to worry about determinants just yet. We want to assume all our data have, each variable is unique, has some type of additional contribution to covariance. It's not a replicate of some combination. Okay. So what happens is the loadings themselves control how related items from the same factor are predicted to be. Right? The loadings, the covariance talks about how related items from different factors happen to be. We talked about that last time. If the covariance was 0, this whole block would be a 0 here. We would expect to find that there were no correlation between items that weren't on the same factor. So now we have to talk about identification. How on earth do we get the factor variances? So what does identification mean? Identification means how do we go and get our numbers out? Because effectively when we're trying to measure something that doesn't exist, it doesn't have a metric. It doesn't have a scale, right? What are the units of happiness? I guess you could sort of you have to define it somehow, right? If you think about physical measurement, we've had to define it too, right? What are the units of length? Well, it depends on, what system you use, but it's either 1 centimeter or 1 inch. Well, I guess that's a unit, I think. right? So we had to define that too. We just have sort of come up with a uniform norm that we've generally accepted, of course, except for in this country. Right? Are there any other countries on the planet that use the imperial system any longer? Like I know in the UK, like there are parts of it that are still there. Like you buy gas in gallons, and you have like mileage on the whatever their highways are, but you don't have like anyway. Never mind. It's sort of there, but not quite. Anyway, same thing happens here. There's no uniform accepted way that we're going to measure happiness or some other latent variable, so we have to define it. We have to define a unit. And the method that we used, that we showed before, was something where we have to define the units. What am I talking about, first of all? We're talking about the variance of the factor, or really the standard deviation. Those are synonymous, right? And we also have to talk about the mean. Right? What's the average happiness for people? What's the average, or what's the variance of happiness, right? Well, one of the ways that we saw before when we made the program on is to put the factor variance set to 1. That is effectively standardizing, or making a standard deviation one. It's like a standard factor, right? It's sometimes we call this the z-score method, because ultimately a z-score has a mean of 0, variance of 1. In this case, for the variance part, setting the variance to 1 means we can estimate all the factor loadings. We can estimate all the unique variances. And this factor is interpreted as being standardized, because its mean and variance are 0 and 1. There is another method, though, and if you're in education, if you're used to item response theory, which we're going to get to in this class, but some of you may have had it apart from here, this first method is used almost exclusively to create a scale, to do measurement with the scale. So the papers that you look at that are defining your scale, they probably use this method in and of itself, because you're trying to basically see the measurement properties of an instrument, but not try to do something with the numbers once you get them. Right? The other method is what we call the marker item method, which ultimately means we need to set one factor loading to 1. When we do that, we get an estimate of the factor variance. Now you're thinking, wait a minute, which item would I use? Well, it's all relative, right? You pick the first item, you pick the last item. You will always, these are equivalent models, right? They fit the same. They give you the same predicted covariance matrix. They give you the same model fit statistics. The only difference is, in this method, you get an estimate of the factor variance. And you have no estimate of an item's loading. And in this method, you get an estimate of all the loadings, but you have no estimate of the factor variance, so it's set to 1, right? So why would you do that? The primary motivation is when the factor variance becomes important. Right? When is it important? When the factor is going to be a dependent variable. Right? So in an instructional equation model, where we talk about path analysis with latent variables, or a bunch of regression equations where sometimes some of the x's and y's are not measured or are latent. When f shows up on the left-hand side of an equals, your left, my right. When you say this factor 1 is equal to, I don't know, beta 0 plus beta 1, factor 2 plus error, I don't know, or better yet, we're going to forget factor 2, that's a bad example. X. We have an observed variable x. If you want to make this regression equation, and this thing isn't measured, what happens is E represents the residual variance of the factor after you've predicted it with what you're trying to predict it with. Right? So if you fit the model, if you fit this model, you'll get one estimate of the residual variance. This is, we'll call this model 2. The other alternative model, or the other model, would be this, which is, you don't have the predictor in there, right? This would be like sigma squared f0, we'll call that, right? Necessarily, the variance for this model has to be greater than or equal to the variance for that model. Why is that?
It's an additive model.
That's right, but it's in a regression model, when you put in predictors, it explains the variation, right? Now, if we have exactly 0 value for the beta weight, it would be equal. That's rarely the case. It's usually some other value, but basically we expect this regression right here. If we want to we even talk about this, we come up with an R squared, right? The R squared for this is sigma squared. It's the difference in the variances over what the original variance happened to be, right? So if we use this z-score method to identify our factor, now all of a sudden, this is equal to 1. Not only that, this is equal to 1. You see, that would cause a problem. So often, whenever we want the factor to be involved in a structural equation model, whenever we want to predict it with something, where does that apply? Well, we might have what's called a higher order factor, right? We might say that we have a set of variables that, that are representing different types of happiness, and then there's one overall happiness variable, right? That's one way. We might have, X might be a dummy code looking at a group. You want to talk about group differences in happiness? You want to talk about group differences in the latent trait you're talking about? That would be it too. So oftentimes in SEM, because SEM is all about trying to do something with the factor once we've created it, we see this marker item method. There.
So you're saying, I understood you correctly, if we have higher order factor, F3, let us assume that this is F3, the equation will be the intercepts plus
The
beta
higher order.
1 of 1, subscript 1 plus beta F2 plus the covariance between the
Not necessarily, but I'll show you that when we get to the end of this. We'll talk about higher order in more depth later. But basically, the higher order is a predictor of the lower order factors.
How do we know, how do we determine which item to use as a marker item? Is that just theory driven?
No, it is completely arbitrary. And it, with the exception of some really extreme cases, it doesn't matter. Because every item that you pick will give you identical fit. And so what am I talking about with this? Let's go back to this, what our model predicted matrix happens to be. We know we get the variance for each item perfectly, right? So if we do the z-score version and we set the factor variance to 1, right? We know what this happens to be. There's three variances, and then there's there's a total of 4 unknowns, but we have essentially 6 equations to find 4 unknowns. If we fix the first item variance to 1, or lambda to 1, then each of these lambda 1-1s, which actually should be lambda 1-1 right here too. Actually, no, right here, all those become 1 as well. And it just flips whatever the magnitude of lambda 1 would have been, gets shoved over to where the variance happens to be, right, accordingly. And so the same thing with lambda 1-1 and so forth. So ultimately, it doesn't matter, with one small exception. If an item has no relationship whatsoever with the factor, right? So if that factor loading was truly 0, then what happens is all sorts of craziness in estimation. Like a factor variance that's estimated to be 18 million times the size of your item variance or something like that. You'll usually get error warnings or whatever else. But that rarely happens. That probably happens in the times I've seen people run CFA for the first time on their analyses. It's probably happened 1 or 2% of the time in my life. Fleeting. So ultimately, it doesn't matter. And here's why it doesn't matter. If you remember when we get to, we go back to our preview of this is the simulation version of the example. If we looked at the output for Levon, remember the standardized values over here? All right. Standardized std.lv gives us what it would have been if we had set the factor variance to 1, if we'd used the z-score factor. Right? So this will always be what it would have done if it was the z-score factor. And regardless of which item we pick, this should always be the same. Right? So there's a metric that we can always describe similarly. Also, std.all will always be the same, because regardless of how we identify it, because we're taking the units of the variable, right, multiplying, we're dividing by the standard deviation of y, and multiplying by the standard deviation of factor. Right? So we're starting to put this all together in that regardless of what we said. And so here again, this is I left this estimate at 100. Remember, we were playing around with this last time, whether the factor variance was 1 versus 100. So each of these estimates with factor variance of 100 will be decimal place will be moved over to 1. It'll be 1/10 the size because the factor standard deviation is 10, and that was 10 times more. But the FCD.LV was the same as we saw before. So it sounds crazy, and believe me, like I spent the first however many years after learning this not wanting to do the marker item version, because it's like how on earth can it be the same? But ultimately, again, remember, these are equivalent models; they fit the same, and for each person's score, what you're doing is shifting. The same order of scores happen, the same shape of the distribution of the factor scores happen. All you've done is just change what is on the the x-axis, what the units are, right? It's still the same. So effectively now what I do in most of my work, I only use the marker item because there's lots of times where I want to use a predictor for the factor, and I've gotten used to it. In fact, it's so much, in the SCM world, it's so accepted. That's the default in Latent. It's the default in M+. I don't know the other programs as well. So it's this hard thing to wrap our head around, especially hard if you're used to just producing instruments just for measurement. If your research is only about developing new scales for happiness or whatever else, it's different. Other questions?
Can we just constrain the factor loading to identify the model?
There's another constraint, yes. If we basically what we're after to figure out the factor variance is we have too many unknowns with the factor variance and the number of loadings we have. So we have to put one constraint on them. The most common version is either factor variance of 1 or item loading of 1. But there's another method. We could take the sum of the item loadings and make them equal to 0. That would be another constraint, right? Or make them equal to a constant. We can make that happen too. All of that happens, and again, it's still synonymous with what we do. There's Todd Little, who used to work in psych. He was a colleague of mine when I was here before. This was not a bad idea of his. I will say there are a number of ideas that were pretty bad, but then again, we all have that. We sort of have to, there's a number of people on campus we have to convince that they're really not what we do methodologically for a lot of what it is. This is fine. This is not one of those because it's equivalent to each of these. It's a one parameter constraint. It's fine. If you wanted to get an estimate of the factor loadings, what you'd do is you'd say this plus this plus this equals 0. Right? Then you get an estimate for each if you really wanted it, plus you get a factor variance. But again, it's a sum to 0 constraint. Okay. How are we doing? Okay. How about the mean, though? Same thing happens. In the z-score approach, the mean is 0. It's standardized. Right? That's this eye of providence, that stupid triangle looking. I don't call it stupid. It was like, oh yeah, when they got to the mean side of the model, they're like, oh yeah, we have means, don't we? Shoot, how are we going to draw those? Yeah, there we go. This thing. If you set the factor mean equal to 0, then you get an estimate for each of your item means. Or we could take a marker item. Remember, item means that's just the, we go back to our model, this is the item intercept I should talk about. Right? If you set the factor mean to 0, you get an estimate for each of your item intercepts for that factor. If you, alternatively though, you could set one of your intercepts to 0 for an item. And then you would get an estimate of the factor mean for that factor. Now that's also all sorts of weird, sort of playing things around. But what this is trying to make you understand is that while the factor doesn't have a scale, if you're trying to give it a mean other than 0, if you're trying to give it a mean other than a constant, you have to get a mean from something. It's borrowing that mean from one of the items. It's not necessarily the mean itself. I go back to, happens here? Well, the expected value of an item, the mean of an item, is this value mu1 plus lambda times the mean of the factor. Right? So what am I talking about? If you're trying to think about mathematically, the expectation of y1 is mu1 plus lambda times the expectation of the factor. Right? That's what that looks like. So what does that mean? Ultimately, our model is going to make this so that it is perfectly equal with y1 bar. Right? Those are going to be equal. Right? The mean of the item and what our model is predicting for the mean is going to be identical. And we can either get it by setting this equal to 0, right? Then it's just mu1. Or alternatively, we could set mu1 to 0, and then we get lambda 1, 1 times the mu for the factor. Right? But what we know is that this thing has to equal y1. Right? So why would we set factor means to be anything other than 0? That's a rarer case than what we see with the factor variances. But there are situations where that occurs. One of those situations happens to be when we're trying to see whether or not our scale is measured the same way between different groups of people. We call it measurement invariance. One of the things we have to tell is whether or not our factor means are identical. Actually, we need to check whether our item means are the same within multiple groups. So one of the ways we have to actually figure that out.
So that'd be like in variance testing, right?
Exactly. Mm-hmm.
So let's say you have the factor means. What analysis do you do to decide if they're significantly different for two groups of people?
Well, there's a series of analyses. You have to get to the difference in the factor means between two groups. It's something like this.
Okay.
But to get here, you have to establish that you have the identical item means for people. You also have to, or at least some of the items are identical. We also have to establish that the factor loadings are identical for the two groups as well.
Okay.
So this kind of cascading series of analyses. You go with essentially factor loadings, item means, sometimes unique variances. And after all that, if you still have a set of items that are equal for the multiple groups, then you do this structural model.
So it's a, how do I say this appropriately? It's some work.
It is definitely some work. But it's all fun. It's a pain, but it is. But basically, why that's the case, though, Craig, is again, the factor means don't exist, and if we go with the idea where we set the factor mean equal to 0, we can't test it because they're always going to be 0, right? We can't. This is 0 for one. This would be 0 for the other. We can't actually do that, so we have to go and give them numbers. But the only place the numbers come from the data. And if we allow the data, if we have to basically constrain it so that the data for the two groups are roughly the same. If it's not the same for the two groups, then we're comparing apples to oranges, right? So that's why we have to sort of build this cascading series of events for it. This is why EFA is popular. It's a hell of a lot easier just to add up your items, do a EFA, and then go put them in a NOVA.
Yeah.
Right? Other questions?
So that assumes model fit's good for the instrument. So
Yeah.
if the model fit is rough,
Yeah.
then you're not going to get to do any invariance testing.
That's right.
What if model fit's rough, but you've made some modification indices to make it acceptable?
That's fine.
It's a
That's
good
fine. Once you get to acceptable, you can still do it. Now the question then is, those modification indices make it so that it's less generalizable as a result,
Okay.
right? You know, people sometimes call the issue in replicable.
Replication
Yeah.
designs.
They call it p hacking. So basically, a mod indice is a bunch of single degree of freedom hypothesis tests, and so you're looking for the ones that are significant, adding parameters in. You're subject to having a term that shouldn't be there get added to the model. You know, it's what common practice is, but I think when you do that, again, it weakens your argument about generalizability for the whole group. If that makes sense. But then again, that's again common practice versus you can make that explicit in your paper. You say, this is what I did. I went through these steps. I know that there's a chance that some of these things I added are not truly significant to the population I'm thinking about, sort of just by chance in this sample or however else. But with that caveat, here's the result. So just acknowledging that up front, and then future researchers would say, let's test Craig's model, and if it was different, see how that works.
Just to clarify, because I'm a little bit unclear about
Yeah.
the idea of marker in the item.
Yes.
You are saying that if we set the item, one of the items to 1, that item or the variance of that item will be passed to the.
If we set the loading for the item,
Yes.
then the factor variance will be will come from a part of the variance of the item itself.
So what about if the scale of the item is different than the variance now is.
Well, what's going to happen if you have a higher variance in item 1 than you have on the others, then the factor variance is likely to be larger. But if the factor variance is larger, we're in a situation like you have now in our example, right? When we have a factor variance of 100 for here, it just makes the loadings look smaller. But when the loadings are smaller, the p-values shift accordingly. Everything is just a shift to where the decimal is, effectively, right? So even if it's a different scale, there are other issues that different scale causes. Numerical stability is one of them. But assuming that that didn't trigger and you didn't have some weird error messages, then these should still be identical. And all it is just shifting where the decimal is and the size of the loading.
Brown talked about the idea that the marker indicator is preferred than the variance of the.
It depends on the background of the person who's working. So Brown's background is more in CFA or in structural equation modeling. If your background is in measurement, if you're trying to build an instrument and provide scores from that instrument and that's it, I would actually say the z-score factor is much preferred because you're getting information about all the items more directly. So if you take item response theory with Billy Skorupski, or if you took it, if I were to teach it, you'd probably never hear about the marker item. Because ultimately, a lot of times we're teaching that class because your goal is to go and put items on and people on a similar scale and provide a score to people that's a factor score. If you're an SEM, you want to do something else with that factor score. Right? But the same does apply there too. We have the same parameters and we can set a marker. So again, here's sort of our options. There's sort of 4 options for identifying the model. Factor mean of 0, factor variance of 1. This is our standardized factor. This is the z-score. This is what we ran last week. Factor variance estimated is where we put one of the factor loadings equal to 1, and we set the factor mean to 0. This is the default in Lavon and M+. There's another method that I rarely see, which is where we estimate the factor mean by setting one of the item intercepts to 0. But we fix the factor variance to 1. We rarely see that one. And similarly, one of the things we actually do see sometimes is the factor variance is estimated by doing the marker item for the loadings, and the factor mean is estimated for doing the marker item for the item intercepts. Let's see this. You want to see the example? I put some numbers to this? Because it's a crazy concept, I admit. This is usually where the CFA lecture crashes and burns. So if you feel like this is crashing, no. While I turn away, raise your hand. It's okay. I can take criticism. I like to think I can take criticism at this. Okay. We'll come back to that. Okay, so here we go. Alternative identification methods is what we have in this example. I'll make sure it's on the screen here so you can see it. The first identification method is where we use the factor mean of 0 and the factor variance estimated. Now, one thing I wanted to note, when I gave you all of the syntax last week, I gave you this very long, where'd it go? Way up here, still going, this long bit of model syntax where I put every part of the model in the syntax, right? There was something for the factor loading, something for the item intercept, something for the factor mean, and something for the factor variance. And I did that because I wanted to show you that you have the ability to manipulate those however you saw fit. We plugged it in to something called the Lavon function. The Latent function assumes that you're specifying everything about the model. That's a lot of syntax. So there's a summary method, or a shortener, if you will, where we can take our syntax and shorten it considerably. And we can do that right up here, where if we specify only the factor loadings, right? We say sit, this is our factor, equal tilde is our saying this is a factor. It's measured by all these 6 items. This is all we need to specify the syntax, and the Latent will go with this SEM function. Will go impose the following constraints. It'll say that all item intercepts are estimated, right? So that is the marker, the factor mean 0 identification method, right? It'll estimate all item unique variances, and it will estimate, and all factor variances and covariances are estimated. So it's actually implying the marker item for the loadings. So one of the loadings gets set to 1 for each factor, right? Factor variances get estimated, factor covariances get estimated, and factor mean is set to 0. So it's that default. So that's a lot easier. That syntax is what I use almost exclusively, unless we have to get into more parts of the model that we don't want to get into right now. So that's pretty nice and tidy. We send it to the SEM function with the same arguments that we gave the Latent function, only now we just give it the shortened syntax. And this is the same output from above. I'll let you confirm it. But let's talk about what happens, though, when we do the factor mean 0, factor variance estimated. Right? So what we saw above was where we did the option on the line here, std.lv equals true. That was the option to standardize the factor by fixing the mean and the variance. If we don't include that, what Latent does, we go down here, is you see this first item. This was under the latent variables. This is where all the loadings were. The estimate of the factor loading is set to 1, and you see no standard error for item sit1r. Right? So by default, it takes the first item of each factor and makes the loading equal to 1. Standard error, not estimated. Z-value. So this, we know this is not estimated. Now you'll note, again, these two columns, std.lv and std.all, are the same as before. Right? So if you're used to one method, you can always look over here to see what it looks like. But then we get down, our intercepts are the same because our factor mean was set to 0. So sit means 0. When we get down to variances, take a look at sit. Variance of sit now is 1.734. Right? So it is now estimated. But under std.lv, you'll see its value is fixed to 1. Right? So that's because we standardized with the latent variable, fixed it to 1. What it would be if we used the z-squared. Now, everything else about the output above us, and even below us, everything we look at with R square is identical. And you can go compare parts of the page if you want to. I won't. I'll spare you the scrolling around. But it's identical. It's the same model fit, same estimates of R square, same standardized columns. It's all good. So that works. Questions on this? Weird, huh? Again, this is just for your information. Just think of it this way. This is just to free up the variance of the factor so that we can do something with the factor in a model. Okay. We have a description of each of these. The next set of syntax is if we wanted to fix the factor loading, have a marker item loading, right? So we're going to estimate the factor variance. But also have a marker item intercept. All right, so what does that mean? We're going to go set the mean of an item equal to 0. And we're going to estimate the factor mean. Why not? Crazy, right? It's going to fit the same. Now, to do this again now, we do need the long form syntax because we have to go and fix the intercept of sit1r to 0. That's what this does right here. And actually, this is where I'm going to change gears a little bit, and we're going to play around with this to try to solidify the representation a little bit mentally. Okay, here we go. So here's our syntax. And again, under the intercept section, you'll see I put sit1r tilde 0. That's its intercept. I could have picked a different item. The fit would be the same. But I'm just picking the first item. You also see 1 times sit1r for the first loading. That means I'm going to take the first item and make it 1 for the factor loading. Make the factor loading of the first item 1. I could have put it elsewhere. The factor variance is estimated by just having sit double tilde sit. And the factor mean is estimated. Now, it doesn't look like it's estimated because it's a 1 there, but that actually means estimate the factor mean. Yes, syntax. So here's the output. Okay. You see our first item has a factor loading set to 1. Now our first item has an intercept set to 0. Right? Okay, so what do we expect the factor mean for the item to be? We know that the intercept is 0. We also know we fixed this loading to be 1. Right? So it's 1 times the mean of the factor. And we know this right here has to equal the mean of the item. So we get mu f is equal to y bar. We just effectively set the mean of the factor equal to the mean of the first item because we've made the loading and the intercept equal to 0 and or 1 and 0 respectively. Right? And if you want to confirm that, let's take a look. Intercept before was 4.443. It's our value. One other thing I want to note to tell that it's the same model, take a look at the log likelihood here. We're going to talk about this next class. This log likelihood, models that are identical have the same number of parameters and the same log likelihood, right? Same data, same people. So I'm going to put negative 11,535.690. And now we're going to play around with the numbers. Who wants to pick the marker item for the loading? Anybody want to? We've got 6 items. Holler out a number from 1 to 6. 3, I heard. All right. Change this to item 3. 1 times. Who wants to pick a number from 1 to 6 for the marker item for the intercepts? Number 6. Someone said it. Thanks for participating. So we do that. We push play. Take a look at our estimates. Oh, we have a little bit different number for our log likelihood. That's the rounding error that we'll end up seeing. But again, oh no, I did it wrong. That's why. The log likelihood, pardon me. It should be the same. What am I doing wrong here? Let's take a look. Hang on here. Oh, I know what I need. So what's happening is, I think what's happening is what Levon is doing is, yeah, it's messing around. It doesn't like to have one of the first indicator where we put a 1. So one way to fix that is to put it at the beginning. That's right. Okay. There we go. So the marker item shows up first. There. This is good information for if you're ever there. Now let's try it. Yes, multiplied by 1. Actually, yes, let's do a 1. There we go. And play. Okay. There it goes. Now the log likelihood is identical. You see how I could already tell originally that it wasn't the same model? Log likelihood. Now we get down here, we see sit3r has a loading of 1, not estimated elsewhere, and sit6 has an intercept of 0, And now we see our factor mean is 9.403. Why is that the case? Because the mean of the item, this is item 6 now, has to be equal to 0 plus the loading times the factor mean. Well, the loading for the item is 0.56. So the mean of the item is 0.56 times 9.403. Right, so or 4 and 4.2. Right, so, but it fits the same. And again, although the order now, SIT 3 is at the front, the order is different. These are identical, the STD LV and STD.all. Crazy, right? That's what happens. Remember, the situational forgiveness does not exist. So we have to sort of make it exist somehow. It's an odd world. But, right there. Yeah. Oh, yeah.
I'm sorry, but
Go ahead, this is good.
so why you? I know that you set the third indicator to be the variance of the third indicator, but why not setting the intercept for the third indicator?
We could have done that. That would have been fine. We could have. But it's arbitrary.
So
And they're separate.
Because in this case, because we do not the mean of the indicators does not include it in the analysis, because what I mean is that when we fix the intercept data, because I think the intercept is equal to the tau equivalence when we go and discuss how to free or put more constraint in the solution.
Right.
So why not putting it in the same indicator? Why
I'm trying to show you that it's arbitrary and it's separate. Right? The factor loadings govern the factor variance. And the indicator, the marker that you choose for it can be any of the items. And independently, in CFA independently, the item intercepts govern the factor mean, and the marker you set you can pick arbitrarily as well, and they don't have to be identical. Right, so because they're separate, they're different parts of the model, because in the multivariate normal, the mean vector and the covariance matrix are independent, you can do either. And have
so this is the purpose, just to show.
Okay. Yeah. Why would you ever do this? I don't think I have a good reason. In practice, what we're going to see for most of the class is we're probably just going to go back to the marker item where we with the default, where we fix the first item's loading to 1, and we estimate the factor variance, and then we output, we set the factor mean to 0, because that's, for the most of our needs, just fine.
But there is no what test for the marker item.
That's right. There's not a test because we're not getting a standard error, right? So we're assuming that this is 1. So right, we're not testing the loading for it. But we don't ever do that anyway for the most part. If it's effectively 0, we're probably going to see a mess it's probably going to blow up our model. And yeah, what you're going to see for most of the things that you do with your own data is that the vast majority of your loadings are going to be significant, because this is the definition that you have. They're going to define the factor as much as possible. There may be 1 or 2 on the fringe that aren't. And if that happens to be one of the marker ones, then you're going to end up seeing the blow up or some weird thing going on with the variance. Okay. Thoughts or questions? Yeah.
So we run several models. I know there's like sometimes the estimated numbers and the STD.LV are the same. Sometimes they're not.
Yes. So up here in the loadings, they should always be the same. When you get down to the intercepts, things are going to start changing, and that's because what we're doing with the STD.LV column, remember the standardized thing that we're doing is we're taking estimate, right? And we're either going to multiply by the standard deviation of the factor, or divide by the standard deviation of the item, right? So STD.all does both of these. STD.LV does one of those, right? And so when you take this mean in this intercepts column, this is sort of a garbage estimate. It doesn't have a lot of inference, but that's where you're going to see these numbers are not going to match the other means, because the mean itself is when we set the marker differently, the means are going to change. Right? We're not doing anything with the mean parameter to standardize though. These other columns for the factor loadings and for the unique variances though, they should line up. Variances may not. The std.all for the variances will line up. I'm not sure about the other one off the top of my head. It's not coming to me right now. Does that help?
Sort of. So basically, we still need to read the estimated number back out.
Okay. This is just like hard to grasp. Totally get it. I've been there. I was there seriously for years. Like when I was in grad school, I didn't bother with the whole marker item thing until I started having to think about teaching SEM, which was like 7 years later, it's like 10 years later, right? So it really is going to matter. We're going to focus on the marker, the default for the most part of the class. Although these early examples, that's actually not true. Okay, we have about 8 minutes left. So can I start on model fit? So remember the model fit, if we fix the identification the same, the model fit should all be anchored around this log likelihood, so they should all be the same numbers for each. So that's how to like get the thing to work. You have to pick an identification method to get the numbers out of the computer. Once you've picked it and you get the numbers out, model fit will all be the same regardless of whether you pick the crazy method that we just implemented or something you're more comfortable with in the CFA model. So let's talk about model fit for a second here. The goal of factor model estimation is to come up with, remember, the means for all the items will be perfectly reproduced because we have this addition thing going on. The variance for all the items will be perfectly reproduced. But where we're going to see model fit discrepancy between our data and our model comes from our covariance matrix of the data. Right? If we think it should be one factor, our Levon will come up with a predicted version of the covariance matrix based on the factor loadings and all the model parameters, factor loadings, unique variances, factor variance. And it's going to compare that with the overall covariance. And because there's no one unified way of doing that, we have 18 different ways to say how close we are to covariance matrix. No question. No. Gotcha. I'm like an auctioneer. Right? At least I'm trying to be like paying attention. I'm sort of it's sort of this weird spot where I know I'm looking at here, but I'm trying to look at your face. It's my diagnostic for how much faster or slower I should go. The other thing you can do to help me out is if it's really bad, like one hand to the head is like this is somewhat bad, but like two hands to the head, it's like that's like slow down, right? But you can do however you want. I don't know. I try to diagnose how well we should go. This is tough stuff, and nobody ever like it's starting to get complicated. But I'm hoping that the pace will help with the complication a little bit. So what we want to do is reproduce our item our observed data covariance matrix as closely as possible, using as few model parameters as possible. It's the idea of parsimony. You've heard of, I've always, whenever it says parsimony, someone says Occam's razor. Have you heard of that? Occam's razor, anyone want to recite? It's the William of Occam. Go ahead, Greg.
Simplest solution is often the best.
Simplest solution is always often the best. I believe, I had to look this up because I like complex models, and then I was trying to publish it, and one of the reviewers was like, Occam's razor, and so I looked it up, and what I found was no plurality without necessity, right? Right, so yes, simplest solution that fits. How's that sound? So we want, if you have two models, like maybe one factor versus two, and they both fit the data, usually the simplest one wins. But if you have two models, one factor and two, and the one doesn't fit the model, you can't even regard that. It's done. It's not even part of the two will win, right? If that makes sense. So we want to do that with as few estimated model parameters as possible. What we're going to use, and what I think the gold standard for what we do currently in CFA and SEM, is something called robust maximum likelihood. right? It gives you good model parameters, good estimates, but it will give us these model parameters in the measurement model. What we call the measurement model, it's again, it's the part where the factor touches the data. It's our item factor, or factor loadings, our item intercepts, and our item error or unique variances. That's the measurement side. The structural model, which is really sort of not a model now, it is a model, but it's just saturated. It isn't like, it's not like what we have this specifically right here. This is a model. But what we're estimating in the structural model is everything to do with our factors, and that would include our factor variances, covariances, and means. And again, that's depending on how you've chosen to identify your method. Okay. So then what we end up getting is when we run Lavon, or we run M+, for every analysis that you do, it actually runs two models. It actually runs three. It runs the model that you specified. It runs the model where it's not even using factors. It's basically going to estimate every mean, variance, and covariance in the data. Right? And it's going to run the model where it estimates every mean, every variance, that sets the covariance is equal to 0. Three different types of models. The reason for that is what we want to do is compare overall, what we call a global test of model fit, is to compare our whole model with those other two models themselves. Right? The model that where it's estimating all of the unique covariances and means. You have a question?
So the Lavon does it for us.
It does. It's in the background.
Oh,
Yeah,
cool.
Absolutely in the background. It's doing three models when you think you're only running one. But the reason why it's running these three is it's going to use a model comparison to see how well your model fits comparatively. Right? What you're trying to see is just globally, again, we call this global model fit because it's effectively saying, I'm going to take one number or a summary of my model, in fact, a log likelihood, and I'm going to conduct a likelihood ratio test to compare my model with these other two. So what am I doing? Why am I saying this? Likelihood ratio test, we mentioned this before. If you have a model, a pair of models that are nested, right? In our case, your model and every model in this class of models, everyone where you're not estimating latent classes of people, one latent class of people, is nested within the model where everything's estimated. All the variances, all the covariances, and all the means. So every model that you can come up with, so long as there's one class of people, is nested within it, right? So now you've got a likelihood ratio test to set up. You're basically saying, is there no difference between my model and the saturated model where the data just are what they happen to be? Right? What you're looking for is no difference, because your model will have equal to or fewer numbers of parameters. And that's where Occam's razor is. If they both fit equivalently well, your model has fewer parameters, you can claim that the factor structure that you have fits the data. Now the other model where you've got no means and covariances, that's like the worst case scenario. Like, okay, my model didn't fit this one. That's sort of like, do I have any factors at all in my model? That's what but we'll talk about that in the next class. So what are we talking about here? Let's talk a little bit about how many possible parameters that we have to estimate for each model. It comes from the number of unique elements in the covariance matrix. The total degrees of freedom, the total possible number of parameters, comes from that saturated model, that one where you estimate everything. Right? And there are this number of total unique elements. Right? We know there's, for however many observed items you have, in this case the number V is an observed item, if you have it'll be V means, V variances, and then V times V minus 1 over 2 covariances. Or if you want an easy formula, it's this right here. Number of variables times number of variables plus 1 divided by 2. That's the covariance matrix. And V, that's the mean vector. Okay, so this is the number of unique means, variances, and covariances total. So if you had a total of 4 items, there would be 14 total parameters. 4 means, 4 variances, 6 covariances. So 4 times 5 divided by 2 is 10, plus 4 is 14. So that's sort of the anchor point. That's the most number of parameters you can put in the model and have it estimated. But even if you put 14 parameters in, it's going to be equal to the saturated model. You're not going to have any claims that you can do. Someone might say, well, yeah, it could be your model or it could be saturated. I don't know. Right? The difference in degrees of freedom comes from the difference in your number of parameters, or difference of the total possible parameters minus the number of parameters in your model. We're going to leave it there. We'll pick this up on Thursday. And I'll tell you right now, no quiz on Thursday. Because I like you, and I don't like the hostility. But then again, if I gave you a quiz, I might just give you the 2 points anyways.
We would do the like this in the quiz.
Yeah. Well, I mean, again, it's more of a, I'm trying to make it more of a self-check type thing. Okay? Less than a penalty. So I'm going to stop here. If you have questions, come talk to me at the end of the class. Otherwise, I'll see you Thursday. Thank you. Do try to read the slides or the handout or the stuff online. I'm sorry, the example online. Thanks, everyone.